Hello friends, welcome to follow up. In this video, we are going to continue our Kahn's algorithm series. In this video, let's look at problem 207, cost schedule. So before we start, let me first give you an overview about Kahn's algorithm. So Kahn's algorithm is a multi-source breadth-first search algorithm. It can be used for dynamical sorting, not for dynamical, for topological sorting. So basically, you can check for a graph whether it's a directed acyclic graph. So this means that the graph contains no cycle, right? So in this problem, so we can model the cost prerequisite relation as a graph. So overall, this problem asks us to check if the graph is a directed acyclic graph. So with that said, let's look at the problem statement. So there are a number of causes. Let's call this number n, right? So labeled from 0 to n minus 1. We are also given an array called prerequisites, where prerequisites I has such a format. And this format indicates that bi is a prerequisite for ai. So we want to return true if we can finish all causes. So in other words, the corresponding graph is a directed acyclic graph. Otherwise, we're going to return false. So I would say for this problem, the two examples here are very special, right? So it's actually, it might be better if we display a more general or more representative example. So anyway, let's look at the two examples. So in the first example, so cost, we can take cost 0 and then take cost 1. So we are going to return true, right? And in the second example, so the first item says that 0 is a prerequisite for 1. Well, in the second one, so it tells us the reverse. Basically, 1 is a prerequisite of 0. So in other words, there's a cycle in the graph. So we're going to return false. So with that said, let's also briefly touch the constraints. So here the number of causes is bounded by 2000, and the prerequisite length is bounded by 5000, and all the pairs in the prerequisites are unique. So with that said, we are ready to look at the code. So in between, we are going to explain the logic. So here, for convenience, I changed the number of causes to be capital N and the prerequisite to capital P. And then let's first look at the coding part. Step 1, we want to make some preparation. So as we know, in the Kahn's algorithm, we have two parts sequentially. One is a graph and the corresponding in-degree information for the nodes. And then it's a traversal, right? So we'll first make this preparation. So in degree, so I'm going to use a dictionary. So for I in range n. And then the graph, I'm also going to use a dictionary, but we want to use a node and neighbor or adjacent list representation. So here I use set, right? So with that said, let's also build this graph and get the in-degree information. So for, let's see, for end, start in P, right? So this means that start is a prerequisite for end. So what we are going to do is graph start. So we are going to add this node end. So notice that both start and end represent causes. So also the in-degree of end is incremented by 1, because this relation means that there's a directed edge from start to end. So we increase the in-degree. So with that said, we finished the preparation. So now let's initialize the queue for multi-source breadth-first search. So for multi-source BFS. So here I'm going to use, basically we use a queue behavior. So we can use deck, but collections deck. So here I'm going to use a list comprehension. So we are going to use cost. For cost degree in degree items if degree equals 0. So this initializes the initial source. So these courses in the queue actually have no prerequisite. We can safely take those courses. So for this problem, we either can get a topological sorting list, or we can get the number of courses we can finish. So for this, I'm going to use n courses to be 0 at present. Then we do the traversal while queue. So first we get the current course. So queue. We want to pop from the head. So we are going to use pop left. So we are going to regard the left as the head, queue head. And then once we do this, it means that we finished this course. So we're going to increment this counting variable by 1. So once we do this, then we can check the neighbors of this course. So for neighbor in graph course, then because we have taken the course, right? So then we are going to decrement the in degree. The in degree of this neighbor is decremented by 1. So because one of its prerequisite course is finished. So now after we finish this, we need to check if all the prerequisites of the current course neighbor are finished. If so, we are going to enqueue this neighbor to the queue. So this in degree neighbor equals 0. So this basically in the problem logic here means if all the prerequisites are finished. If so, we are going to append this neighbor, right? So then afterwards, we just need to return if the number of courses we can finish equals the total number of courses, right? So with that done, actually this forms a solution format to this problem. So now let's do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the cases. So here, let me make a comment. First, so for this problem, we can get a topological order. So we can get a topological order. Let's see this. So each time we finished a course, so we can do topological append, right? This course. So later we can print out this topological list. So we can do this. So for this problem, so we can have 0 and 1, right? So in general, I would like to remark that topological sorting order is not unique, right? For example, let's use, so we need to finish course 2 to finish 1. And also we need to finish course 3 to finish course 1. Then the topological order can be 3, 2, 1, or it can be 2, 3, 1. So this is just a very simple example to demonstrate the non-uniqueness of topological sorting order. So this is the one thing we want to notice. Another thing we want to notice that, so in the traversal, typically we need to use a dictionary, a set to help avoid visiting a node repeatedly. But here we are dealing with directed graph, so we do not need that, right? So similarly, if you do traversal for tree, you just need to retrieve the left child or right child, or correspondingly the left subtree and the right subtree. You don't need to use set. So that's the second comment. So with that said, basically that's about it for this current video. So you are welcome to check out other videos for this series. Thank you.